This video introduces the ideas of tautologies, contradictions, contingencies, and logical equivalences. A compound proposition is a proposition made up of propositional variables. These are letters like P or Q or R that represent simpler propositions, and logical symbols like and, or, not, etc., that connect them. For example, the proposition P implies Q and R would be a compound proposition. A compound proposition is called a tautology if it is always true, regardless of the truth values of the propositional variables inside it. Let's show that the compound proposition P and Q implies P is a tautology. We'll do that using a truth table. I'll make a column for P, a column for Q, a column for P and Q, and finally a column for P and Q implies P. P can be true or false, Q can be true or false. So these are the four possible combinations of truth values for P and Q. Now P and Q is true when both P and Q are true in the first row, and is false in every other situation. P and Q implies P is going to be true when P and Q, that expression is true, and P is also true. So we get a true here. And it's going to be true anytime this premise P and Q is false. So it's going to be true in the next three lines. Therefore, the expression P and Q implies P is always true, regardless of the truth values of P and Q, and so it is a tautology. A compound proposition is called a contradiction if it's never true, regardless of the truth values of the propositional variables within it. Pause the video for a moment and see if you can show, using a truth table, that this expression is a contradiction. I'm going to start my truth table with a column for P, a column for Q. I'll make a column for P and Q. Let me put a column for not P and one for not Q. And I can make a column for not P or not Q. And finally, a column for the entire expression P and Q and not P or not Q. As before, there are four combinations of truth values for P and Q. P and Q is true when P and Q are both true and false otherwise. Not P flips, I'll just flip the truth values for P. Not Q has the opposite truth values as for Q. And now not P or not Q, that's false for this first row and true for all the other rows. Finally, if I want to find out the truth value for this expression, that's going to be true when this expression P and Q is true, and the expression not P or not Q is also true. And if you look at each row, we see that it never happens that both of those parts are both true. So therefore, this expression is always false. We have a contradiction. A compound proposition is called a contingency if it is sometimes true and sometimes false. That is, it depends on the truth values of the propositional variables. I encourage you to stop the video and use a truth table to decide if this compound proposition is a tautology, a contradiction, or a contingency. I filled out the first three columns of my truth table. Now to fill out the last column, this imply statement is going to be true when the premise is true and the conclusion is true. So in the first line, it'll be true. It'll be true in the second line for the same reason. It will not be true in the third line because in that case, the premise is true, but the conclusion is false. In the last line, it will be true because an if-then statement is always true if the premise is false. So we see that we have a contingency because the truth value of our compound proposition depends on the truth values of the constituents. It's sometimes true and sometimes false. Two propositions R and S are said to be logically equivalent, written with this triple equal sign, if the compound proposition R, if and only if S, is a tautology. Always true. Well, remember, an if and only if statement is true when both of the pieces are true or both of the pieces are false. So for this to be a tautology, it must be that R and S are always either both true or both false. If we think of R and S themselves as being compound propositions, we're saying that R and S are both true for the same truth values of their constituent propositional variables, and both false for the same truth values. Practically speaking, this means their truth table columns look the same. So let's use a truth table to determine if these two propositions, P or Q and not P implies Q, are logically equivalent. I'm going to start by building a truth table for P or Q. And now I'll build a truth table for not P implies Q. And we see that for the same truth values for P and Q, we have exactly the same truth values for our two expressions. Their columns look identical. I could go a step further and build a column for P or Q if and only if not P implies Q. Since if and only if is true when both of its constituent pieces are true, like in the first three rows, and an if and only if is also true when both of its constituent pieces are false, as in the fourth row, we see that this if and only if expression is always true. It's a tautology. So we know that P or Q is logically equivalent to not P implies Q. In practice, I rarely go to this last step because this last step will be a tautology. It will be always true as long as these two columns have the exact same truth values in them. In this video, we use truth tables to determine when a proposition is always true, always false, or sometimes true and sometimes false. We also use truth tables to determine logical equivalences by checking if two columns of our truth table look exactly the same.